Okay, sorry I'm late. Let's get started. So we're going to finish off the core software for CUDA today. So at the end of this lecture, you'll have at least a pretty good picture of like what basic CUDA programming looks like. And we're going to segue into some background on machine learning and then into the core computations that happen on many machine learning workloads. And then we'll segue into how that actually maps to a GPU, okay, in modern machines when we, do deep learning at scale, which is what everyone is doing today, and to some extent. But before we get there, let's finish off with sort of generalized CUDA. So we ended on this slide where we're just talking about launching concurrent kernels. You're basically able to launch many kernels in parallel if they don't all take up all the GPU. CUDA has evolved. This slide is old. We will get to the more advanced features of CUDA when we go into the sort of machine learning side of the class. But it started out as just C and a subset of C that you could support, right? Like a very limited, you couldn't have, I think they've had function calls since the beginning, but you couldn't have like objects with virtual functions and all this kind of stuff in the beginning. And then they've added more support for more C++ like coding on CUDA as it's sort of evolved. And some things that are sort of somewhat interesting that you guys have played with a little bit, at least one of them. One is that you're actually able to launch kernels from the GPU. So there's this thing called dynamic parallelism, where you, inside of your kernel, if you try to do that like triple less than, triple greater than thing, it'll work. And it'll try from a GPU thread to spawn a new kernel. Now, you can imagine that if every thread in your 60,000 thread kernel tries to spawn its own 60,000 thread kernel, things aren't going to work very well. So why would they ever add support for this? So it helps if you have an algorithm where the amount of parallelism in the algorithm is growing dynamically. Like you start out with only a small subset of threads active. Those threads will then spawn more threads, which may spawn more threads. But as a programmer, if you're using this feature, you have to be very careful about like how big that grows, because otherwise it gets too big too fast. It's not pervasively used because in practice, if you have such an algorithm, it's, the trade-off between just going back to the CPU and spawning another bigger kernel as opposed to launching it dynamically from the GPU is not really as, it usually works out to be better to go back to the CPU and spawn it rather than try to spawn individual GPU threads. So there's not a lot of code that actually makes use of this, but it is a convenient programming feature. And, if you're trying to create some kind of dynamically parallel application, it makes it a lot easier to code up as opposed to like having to restructure things. Yeah.
Isn't it used in ray tracing?
Do they spawn new kernels? I don't know if they don't really do it this way because the overhead of doing this is large. Okay, because if you think about what needs to happen to spawn a new kernel, you have to go to some global controller that is, managing all the queues of all the kernels, because there could be kernels coming in from the CPU, kernels coming back in from the GPU. So you have to go out to this global structure that the CPU also shares, right? So there's some inherent synchronization that needs to happen. And then you have to go through the whole process again of redistributing the work, et cetera. In something like ray tracing, where each individual thread is spawning new kernels or spawning new work, it's usually handled through a mechanism called persistent kernel or persistent threads, where you don't kill a thread, but like you basically have some shared work queue that they're all pulling from. And you can do this in a hierarchical way to make it much more efficient. So ray tracing kernels have been around long before this dynamic parallelism thing. And if you're clever and you want to go through the headache of like managing the parallelism yourself in your CUDA code, it's usually more efficient to do so. But this is just pretty damn convenient, right? Because I can just spawn kernels in the same way I would have if I went back to the CPU. But the reality is that it usually ends up being not as good a performance as if you can hand tune it. Yeah.
I know for like the optics API or like the ray tracing code,
Yeah.
they completely disabled dynamic parallelism and shared memory.
Yeah. Oh, even shared memory?
Yeah, it's like you can't use it.
Probably because they want all of the memory to go. So are you saying for the ray tracing cores?
Yeah, like if you use optics
With ray
and launch
tracing?
a kernel, you can't use shared memory. And I think it's also because they like recently introduced like what's it called, like shader execution reordering.
Right.
So you can dynamically like move threads across warps to prevent stalling, and that they do through shared memory, like behind the scenes.
In the ray tracing.
The ray tracing.
Yeah. So ray tracing, but that's a graphics workload, right? You can't even access you can't, there are no sort of, okay, we'll talk about the instruction set in a minute. So there's basically you can sort of think of your GPUs as having two different instruction sets, one that is compute centric and one that is graphics centric. The compute centric stuff you access through CUDA. You cannot even access the ray tracing units through any CUDA interface today.
Right, I mean, even like shared memory if you're writing like a ray tracing kernel.
Correct.
That like calls something that offloads it to the ray tracing core, that kernel itself can't use shared memory.
The kernel that spawns something that goes to the ray tracing?
Exactly.
Yeah, it's possible that they carve out some fraction of that shared memory to basically do the buffering that's necessary for the ray tracing unit. Because that thing is, I mean, we'll talk about it a little bit when we get into the hardware side, but it's doing a bunch of buffering and reordering of threads, exactly as you said, to try to mitigate this dynamic parallelism bit, but not dynamic parallelism, but this sort of, they call it ray incoherence. It's when rays go off in different directions, right? Which is that's equivalent to like memory and branch divergence in normal CUDA code. So there's a bunch of tricky mechanisms for ray tracing to try to make that better in hardware. And I'm guessing what you're saying is that I don't know why you do this, right? So you've written a CUDA kernel that's going to then spawn something from optics.
Yeah, there's like a specific function called optics, like ray trace or ray watch.
And you do that from the CPU or the GPU?
You do that from a GPU kernel. So inside the kernel, you call that. But
inside a CUDA kernel?
Inside the CUDA kernel. So everything else you write in the CUDA kernel just runs on your SM.
Yeah.
Just that one function call.
Okay, that's interesting. I didn't know that was actually available.
Yeah, it's good. Okay. I work with like Millens.
Yeah, oh, you're in Mellon's group? Okay. I didn't know that they poked a hole in the CUDA interface for this. Last time I looked at it, you couldn't. Like you had to use optics or you had to use a graphics kernel, but I didn't know there was a CUDA. You and I should talk actually. But okay, so for those of you who are not sort of like super into ray tracing, there are additional restrictions or specialized units for ray tracing on these things now, and we'll talk about that as we sort of get into the later parts of the class. But they don't use dynamic parallelism. There's no chance that NVIDIA has like rolled out their own libraries that use dynamic parallelism because the overheads are just too high. People have done research on like, okay, if it's bad to do it at a global structure, then what do? Well, you do it hierarchically. So you spawn a kernel, you have a sort of local kernel scheduler on each SM that will handle sort of self-spawn kernels and try to keep them local to avoid the sort of global synchronization. And you can play sort of games like that to try to make that more efficient. So you can play with this. It's kind of fun to do to like spawn kernels from kernels, but generally, if you really have a high performance workload, you don't use it. The other thing that began as a programmer convenience feature is this thing that you have used called unified virtual memory. This has been around for about, I guess 7-8 years now. And it basically gets rid of all of your mem copies, right? All that CUDA mem copy it back. You don't have to do that anymore. You can just call this one CUDA malloc managed call, and then essentially it will carve out a space in the CPU's paged or pinned memory space. Pinning means that it won't get paged to disk. Okay, so the CPU will say this, if I did this CUDA malloc managed on 4 GB, then I will go to the CPU, And the CUDA drivers will go behind the scenes and say, give me 4 gigabytes of pinned memory, meaning you're not going to page this out in a normal virtual memory system. And then it will reserve that in the CPU side, and then the GPU will access that memory with the same pointer, even though it's not the same physical address, because the GPU still has to ultimately read everything from its device memory. But there's an automatic paging mechanism that will move the data from the CPU's paged memory into the GPU's device memory, and then manage that space in, sort of a quasi LRU fashion with prefetching, et cetera, just like you would a sort of normal virtual memory system. But instead of being between the DRAM and the disk, it's between the GPU's device memory and the CPU's host memory. When this first came out, it was absolute crap. I was an intern at NVIDIA when this came out, and they had performance studies on like just not doing the explicit mem copies, and it's like a 4x slowdown or something versus just doing mem copies. But they've made the prefetchers better. They've made them more intelligent. So now I think you measure this in one of your assignments, right? That you probably already done or are doing. Is that still true or not? You guys didn't measure this? Now it's only like, a couple percent slower to use the virtual space rather than just do the CUDA mallocs. In sort of traditional copy everything, do the work, move everything back workloads, this gets worse as you get into more, nuanced workloads or workloads that are stressing capacity, et cetera. But it's not as bad as it used to be. So you haven't used this CUDA malloc managed? We don't make you do this in the assignment. The team must have ripped that out. Okay. So you all had to do the CUDA mem copies, CUDA mem copy back in the assignments you've done so far. Okay. But you don't have to. You can use this thing. And it's kind of interesting to see what happens if you just change it to use the virtual pointers to see if it, how much worse it is. One sort of consequence of this is that since you don't have explicit mem copies, when you call the kernel, you actually have to synchronize afterwards. Because remember, your mem copy was, the synchronization boundary because it was a blocking call. And if you call this kernel, so in this, little CUDA 6 piece of code, right, I called qsort. And then I was trying to use the data that the GPU produced on the CPU in the sort of second last CPU line there. But if I don't do CUDA device synchronize, since the kernel calls are asynchronous, it's gonna go off and run the kernel, and then the CPU is gonna go try and use the pointer for the data that's not actually produced yet, and it's gonna get garbage results. So you have to explicitly put the synchronization in there because the mem copy was doing that for free for you before. Any questions on these mechanisms? Okay. Okay. So we're going to talk a lot more about this, and these have sort of evolved a lot. So CUDA 7 and a bunch of C++ stuff. So like, anyone who's, what's the current version of C++? 17, 18? Who's a programming language person? 21 or something like that. What is a bleeding edge version of C++ these days?
26.
26. Okay. So they're not, CUDA isn't, and 11 was several years ago. CUDA 7, like, supported C++ 11. I don't know what the hell they do to C++ every time they rev it. I don't check, but like, they're materially changing the language. You can, you can say auto now instead of like int equals, right? Like, there's all these sort of things that they're adding this syntactic sugar to the language to make it more usable. So Python doesn't make it irrelevant, I guess. But, yeah. So anyway, so NVIDIA just is constantly trying to keep up with whatever the C++ folks are doing, but they are sort of materially behind, but always sort of trying to make it better. They also added support to actually oversubscribe the GPU memory. So that virtual memory system before, it was only really a programmer convenience. You couldn't, for example, CUDA malloc manage 100 gigabytes if you only had an 80 gigabyte card. You can do that now. And then the underlying system will automatically page in and out the data as needed, which is quite convenient and similar to how conventional virtual page systems work. And then CUDA 9 was tensor cores, which was really a big one, where they added specific matrix multiplication units inside the cores themselves to make machine learning work better. Okay. This is just sort of a marketing picture. We'll talk a lot more about these cores when we move into how machine learning kernels are implemented. But basically, they operated instead of operating on, sort of conventionally scalar pieces of data in each thread, they're loading data in a matrix form. Those matrices are loaded into what you can effectively think of as matrix registers. And then those matrix registers are read by a matrix unit that will perform the matrix multiplication against all of those sort of units in the block, boils down to sort of fuse, multiply, adds of matrices. And every optimized library that runs machine learning uses these things because it's much more efficient to run them on the tensor cores than it is on the conventional SIMD units. So this sort of all came out in the same time frame as the TPU. Who's heard of the TPU? What does it stand for? Who developed it? Google. Okay, so Google, like basically the landscape was Google was buying a bazillion GPUs, right? This is why the stock went like this, because they had to have GPUs to basically do training and inference for machine learning. It was costing them a huge amount of money because NVIDIA could charge them whatever they wanted. It was sucking a huge amount of power because GPUs are more power efficient than CPUs, but they're still not more power efficient than something that only does matrix multiplication. So they decided to sort of grow their business vertically, right? You maybe heard of this if you're a business person, right? Google traditionally did software web search, right? So they went out and they hired a whole bunch of engineers. Does Patterson still work there? He used to for a while. I think it was in the Google Brain project. So the guy who did the book for 565, like they poached him from Berkeley. They hired a whole bunch of hardware engineers to go and build, a specific accelerator, and they continue to sort of rev this thing that is focused on basically just doing gem operations. That is the TPU. We will read the TPU paper in this class. Did anyone read this paper before? No. So it's an ISCA paper from like 2017. It doesn't read like a traditional, academic paper because it's written by industry. So it reads almost more like a product brief, but it's kind of, it's interesting. And it gives you a sense of like what they actually built, which is kind of cool. So in the beginning, also the precision on machine learning has like floated around a lot. Like when your whole workload is dependent on doing matrix multiplication, there are only so many games you can play to make that better, right? One game you can play is to reduce precision. So if the algorithm is tolerant to you having a smaller floating point precision, or even just going to some integer value like int4, int8, then you can save bandwidth, you can increase compute density by simply just shrinking the precision of every operation. And in the beginning with tensor cores, you could start out by basically doing FP16 by FP16 that would produce an FP32 matrix as a result. Now they're super configurable, and they have all these bizarre data types that are sort of targeted at machine learning workloads that generally will tolerate, especially during inference, a very low level of precision. So that's one game you can play to make dense matrix multiplication better. What's another game you can play? Let's say that I've like optimized my kernel and I am at peak max flops. Okay, I'm at max flops for whatever the heck I built. I can shrink the precision to make max flops, not flops, but ops, right? If you look at any machine learning documentation now, they don't say like, this machine has this many flops. They say this machine has this many tops or ops, right? Because they're not actually floating point operations anymore. They're like int4 operations. And of course, you can quadruple your throughput if you just shrink everything by a factor of 4, right? So if I'm already there, if I've already like kept my ALUs as busy as humanly possible because I've tiled the hell out of this thing and I'm able to keep them at like 98, 99% efficiency, what else can I do? This is the other major thrust of what games people play to make matrix multiplication better. Yeah.
I don't know if this is exactly what you're talking about, but I saw a video last week about like optimizing the matrix multiplication algorithm.
Yeah. So you can change the algorithm. We'll talk a bit more about that in the class. So you don't just do the traditional algorithm. There are other algorithms that are actually algorithmically more efficient, especially depending on the data type. Bizarre things like Winograd. Has anyone ever heard of Winograd? It's this ancient sort of different way to multiply matrices from, the 60s, 70s. It turns out if your data is shaped a certain way, that's actually better than doing dense gems. So you can play with the algorithm. What else could you do? One word, exploit sparsity. Thank you. Dense matrix multiplications are assuming that every value is good. If I have trillion parameter models like traditional, well, not traditional, like modern machine learning has, most of those values, or at least significant fractions of those values, are going to be 0 or very close to 0. And if I throw a dense matrix multiplication, accelerator at this thing, it's just going to be computing zeros all the time, right? If like 3/4 of the elements in that B matrix are 0, and 3/4 of the elements in the C matrix are 0, then the result's going to be 0. And I did all that math for nothing, right? So it looks good on paper. Yes, I've got all these tops, but half my tops are just computing zeros. Their values very close to 0 that maybe I could just call 0. And in machine learning, sometimes that's better, right? This phenomenon of dropout, like trying to take out certain weights when they start to get really small, actually ends up, materially making the accuracy of your model better. So once we've sort of optimized dense gems as far as they can go and reduced the precision as far as the algorithm will tolerate, the sort of last great hope to make these things faster is sparsity, is that not all of the values are going to be, relevant. And now you end up in sparse matrix multiplication, which is much more irregular than dense matrix multiplication, because you don't know what the zeros are fundamentally at runtime, right? The zeros are created dynamically. If you know where the zeros are, like in the filters, right? So those of you familiar with machine learning, if you know some of the weights are zeros, you can do pre-processing on it and then sort of compress it in intelligent ways. NVIDIA actually does this. They have a new unit called the sparse tensor core. Who's heard of this thing? Nobody? I thought you guys would be much more into machine learning than you are. I thought you guys would just be, this is boring. But okay, so there's these tensor cores, right, that are designed for dense gems. But, sparsity is one way you can try and make these operations more efficient. And so they've created sparse tensor cores, which are specifically targeting sparse matrix multiplication. And they effectively do this by doing some pre-processing on the weight matrix. So this is really only possible during inference. After you know what the weights are, you pre-process the thing, create a specific sparsity pattern, and then your machine gains 2x efficiency because you can drop half the operations, okay? So these are the kinds of games that you can play in machine learning acceleration, and we will look at these as we get deeper into the class. But the tensor core was sort of the first material thing inside a GPU that they added specifically to accelerate machine learning workloads, okay? Before that, it was all graphics-specific hardware, of which there's a lot, and then additions to try and make the general purpose side much more performant. And then they were like, oh, crap, everyone wants to use these for machine learning, and Google's making its own thing. And, our SIMDs aren't going to be as efficient as this TPU. We need to basically go part way on a TPU and put you could sort of think of it as like little TPUs inside. The design is different, but sort of materially kind of the same idea. Put little TPUs inside of each SM, and then we can sell these things and compete with sort of specific gem accelerators. Questions on this? Yep.
What's the advantage of putting tensor units on a GPU versus just making a dedicated GPU?
So from a 10,000 foot academic perspective, not really much, right? Because now I'm saddled to all this silicon that is not really doing gems, right? They still tape out, the texture pipeline, for example, right? That could be used to make a bigger shared memory or a bigger, tensor unit. So from a sheer, am I using my silicon for the purpose that this particular machine is mostly used for perspective? No, you're better off being more specific. But from a programmability perspective and from an economic perspective of, I don't really know how things are going to change in the future. And I don't want to buy a bunch of machines that work fantastically well for algorithm X. And then when the next NIPS paper comes out that says Y is actually way better than X, I've got this machine that doesn't work. That doesn't happen to a GPU, because you can always fall back to some super data parallel implementation. As long as you've got the parallelism, some ninja can write the CUDA to make it work. And it's going to be better than the bespoke accelerator that it won't work on, and it'll be better than the CPU. So I would argue that it's really the sort of generality of these things that has made it much more economically palatable for companies to pay what they're paying for them, because they know that they can change the software and, it's going to work reasonably well if the algorithms change. I mean, there's also, economies of scale and, the fact that because they are sort of selling a lot of these things, they can make them more efficiently. Like the process node other people can use the SNC too, but NVIDIA's, at the bleeding edge of the process node usually. So, and just marketing and, sales factors. I mean, these things sort of matter, right? But if I built just a machine learning specific accelerator, you could out-compete the GPU, right, on certain workloads. But it's also hard to keep up, right? Because there's a huge economic machine that's putting up the next generation of these things that you know, if you want to do a startup or something, it's very hard to get out before the next gen comes out and then beats whatever you've done. Yeah.
Also, the ISA and the whole software stack matters a lot, right?
Yeah. So it all supports PyTorch, all of this, you know, machinery above the core hardware is supported and fairly easy to use, right? And, you know, NVIDIA has sunk a lot of money into supporting this sort of detailed software stack. And if you're going to build your own accelerator, you know, we tend to be hardware people here in ACE, and we sort of say, software, who cares? But like, that's actually pretty damn important, right? The thing has to work, it has to be stable, it costs a huge amount of money to build up a software infrastructure. And it's not like NVIDIA is open sourcing this so anyone could use it. They sort of keep it inside so you can't just take it. So, you know, that's also a factor. Just the software stack is an inertia associated with that. Other questions? Yeah.
Is the design of TensorFlow proprietary or is it like
You can't look at the RTL. Okay. But you can sort of infer what's going on. And the part of the ISA that programs these things, or at least a higher level ISA, which we'll get into, is documented and sort of visible. You can reverse engineer the lower level ISA. We have done that. And you can sort of get throughput latency numbers out of this thing that give you a pretty good estimation on even energy numbers if you sort of play appropriate games. To get a sense of, at least, it's not open, but people have banged on these things enough to have a pretty good idea of what it looks like. Okay, good question. Other questions? Yep.
How exactly do you exploit sparsity? Is that more on the software side or more on the?
So, I mean, people are playing all kinds of interesting tricks to try to exploit sparsity. The way that is commercially available right now is a combination of software and hardware. So I take my weight matrix and I know that it's sparse, or I intentionally create sparsity in it in a particular pattern. So 2x2 sparsity, I think, is what the sparse tensor cores in at least the last generation did. So basically you'd have two elements that are good, and then the next two elements, you're going to have 3 or 0 in the filter matrix. And then you feed that into a unit that knows that this thing is compressed in this 2x2 fashion. And then you've got another matrix that isn't sparse, right? So this is a one-sided sparsity problem because the activations are flowing through. You don't actually know if these are sparse or not. And then the unit is designed to, you know, given this particular pattern, like do the math that you should have done and efficiently write the result out to the sort of non-sparse output matrix. So it's a combination of software, pre-processing, and hardware to try to take advantage of the fact that you know this particular sparsity pattern is there. There's been other works that have tried to take more advantage of dynamic sparsity. That becomes trickier, becomes more like traditional CPU type microarchitecture where you don't know, like if the branch is going to be, you know, go like taken or not taken. So you have to do some level of, you know, cleverness to try to react or predict these things, and with varying levels of success. So I think there's still a space here on trying to exploit sparsity in interesting ways. The way that it's economically done is a combination of, you know, software preprocessing and sort of not dynamically changing hardware, but hardware that knows how the software is going to change the data to make it more efficient. Other questions? All right. Okay, blah, blah, blah. So ISA. So it stands for Instruction Set Architecture. Every machine has one. NVIDIA, AMD, and I believe all the other major GPU vendors as well. I think Apple has an intermediate ISA. They sort of, I don't want to call redefine, but sort of change the way that we traditionally think about ISAs. So they created something called a virtual ISA, which is like an intermediate representation. So compiler people, what's an example of an intermediate representation? LLVMIR, right? That's basically LLVMIR. For those of you not familiar, you can take any program that's written in any language, and then you can compile it down to LLVMIR, and then I can take LLVMIR and then target any of the, like, you know, the actual specific ISAs of whatever machine I want, right? This is what makes compiler engineering tractable, right? You don't like have to say every time a new ISA comes out, I have to work all of my optimizations and all of my entire compiler chain. I don't. I just have to know how to take LLVM IR and then generate the specific ISA for this particular machine. So it's like many languages come down to LLVM IR, and then they can do transformations and optimizations on LLVM IR, and then spray that out to many different potential ISAs. That's why you can run GCC on, you know, a Mac that was x86 or a Mac that is Apple, and it's transparent to you. And it's basically the same compiler toolchain. It's just that it's using a different path to generate a different specific ISA. So it's essentially a layer of indirection. That's what an intermediate representation is. And historically, this happens during compile time, okay? So you don't see the LLVMIR in the executable when you compiled your CPU binary. You just see the x86 instructions. You can object dump the thing and you can see them. For GPUs, they've added another layer of indirection. So they're still doing LLVMIR, but then the LLVM won't target the specific machine ISA. It'll target another virtualization layer called the virtual ISA. And for NVIDIA, this is called PTX, or Parallel Thread Execution Language. There is very good documentation on this. So you can go look up the PTX definition. It will tell you every instruction that's inside that virtual ISA. It'll give you the functional definition for everything it's supposed to do. If you look at the composition of the ISA, it's a lot like traditional reduced instruction sets, like, you know, RISC-V, right? If you compile a very simple program that's doing like loads and stores and adds and multiplies, it looks very similar to a RISC-V or an ARM-based, you know, compile program. There are some weird, funky SISC instructions in there, especially for things like tensor cores, et cetera, but the sort of core base of the ISA is mostly reduced instruction set. And one consequence of this is that they don't actually have to do register allocation for every thread at compile time. And there's good reason for this, because they actually are going to change the amount of registers in the architectural ISA depending on how many threads are running and depending on what generation of the machine you're using, okay? So the way this works is that you run NVCC, you get a binary. Inside that binary, there isn't necessarily the actual machine instructions that you're going to use on that particular GPU. Inside the binary, there is this virtual ISA. Then when you go to spawn your kernel, the driver will pull out that PTX chunk from your executable binary. It'll run it through a secondary compilation step that they call the finalizer, and that finalizer does additional compilations to take that PTX and turn it into the actual machine instructions that this particular machine understands. So this has several benefits. One is that I can compile a binary for, you know, a Fermi machine, which is circa 2009, and I can load it in an NVIDIA driver that was released yesterday for a Hopper machine. And the finalizer will make sure that, and the ISAs for these two machines, the actual machine ISAs, are drastically different. In the early days of CPUs, they were super CISC type ISAs, more looking like what graphics look like. Today, the actual machine ISAs are very similar to, you know, the sort of RISC ISAs that you're used to. And I can transparently, to the person who compiled that program, I can just translate that virtual ISA into the actual machine ISA. So you have infinite backwards compatibility. And you can change your ISA in any way you like, the actual machine ISA of the machine, and you don't have to rev the binaries, which is the sort of hell that Intel and AMD have found themselves in with x86, because once you have a contract that is the ISA that says, I support all of these instructions, you have to support them forever. And you have to be able to parse binaries that were generated 2 decades ago and have the actual machine instructions, the ones and zeros, run on that particular machine. Okay, so to not hamstring themselves to this legacy and allow them to have a lot more flexibility when they change the underlying ISA of the machine, they introduce this virtualization layer. Questions on this so far? Yep.
Is the finalizer a purely software construct that has software drivers that NVIDIA creates, or something like that?
Yep. This is it's basically another step of the compilation, and you'll find that if you look. If you're a compiler person and you're looking for how the code is transformed and how many optimizations are performed, there are optimizations performed at the PTX level, but then there's a lot of other additional optimizations performed, like additional loop unrolling, additional transformations, et cetera, applied at that finalization step. So it is basically a compiler inside your driver. And you can force NVCC to do this beforehand, because there is an overhead to do this, right? When you spawn your kernel, when I do those triple bracket things and I invoke it, and it starts the whole machinery of trying to get this thing on the GPU, you're invoking a compiler. There is a latency associated with that. Generally, GPUs get away with this because they can hide that latency and the long latency of just sending anything over to PCIe. So you basically get spare time to do this compilation, while you're spawning the kernel. And then they cache it in memory, so the next time you spawn it, you don't have to recompile it or whatever, right? So because of the execution model being naturally latent, it was sort of free for them to put this secondary compilation step in, and you don't really feel it. But if you have a super big code, or you're launching like a lot of kernels in succession, this sort of compilation time can start to hit you. So you can tell the sort of static compiler, I want you to compile this for Volta, Fermi, Pascal, Hopper, and then it will bundle into the binary. Your binary will just keep getting bigger, right? So it'll basically have different ISA implementations of every different ISA you want to target. And then when you spawn it, it doesn't have to do the compilation. You can just go straight to the code. But yeah, effectively, there's like a little compiler inside of the drivers. Yes, go ahead.
And then just a follow-up
Yeah.
question. If NVIDIA is really trying to hide their ISA,
Yeah.
would it make sense then to have basically like a compiler within hardware, essentially, to be able to get like a higher level binary?
You could.
Parse out some of that and change it to their own ISA?
That's effectively what x86 machines do with micro-ops, right? Where you've got, right? And, your x86 machine doesn't really run all of the x86 instructions. There's like a little compiler that is very simple because it's in hardware that decodes those x86 instructions into micro-ops, which look very risky. GPUs don't do this because they sort of don't have to, because they already have this compilation step in the middle anyway. So why would I waste silicon and latency and energy in hardware to do this translation when I can just do it in my finalize? So it's given them a way to essentially do micro-op-like stuff. It's still visible because you can look at the ones and zeros, and trust me, people have and reverse engineered what it's doing, which is a huge pain in the butt, but it's doable. But in practice, it's really hard to exploit this, and no one really has if you're thinking about trying to keep it secret. Okay, good question. Other questions? Okay. Anything else of relevance in this slide? Yes, register allocation. So this is a pretty important problem, especially on GPUs, since registers are the shared resource. When you compile a CPU program, your ISA defines an architectural set of registers, and that's all you get. Like you only have R1 through R32 or whatever, depending on what ISA you have. In GPUs, they can grow the number of architectural registers that every thread has based on the parallel demand for those registers. So if you only need 12 architectural registers, that's all it will give each individual thread. And then as a consequence, you'll be able to run more threads. So there is this trade-off between how many registers you expose at the architectural level and the amount of parallelism you can get on your core, because remember, that big pool of registers is shared between all of the warps that get scheduled to the SM. So there's this kind of interesting trade-off on like trying to make codes more efficient by giving them more registers versus parallelism of having more threads, because now you've got more sort of work being done in parallel. A consequence of this means that if you look at PTX, it has an infinite register set. It does SSA, which is single source assignment, right? Compiler people, that's what that stands for, Bill student, which means that every time I need a new register, I just take one. So you look at PTX for a big code, they'll be like register 10,000. And of course, the machine doesn't actually have register 10,000. So during that finalization step, it's up to that finalizer compiler to then register allocate the thing and say, all right, for this kernel, I know that I'm only going to give it 20 registers. So now if I need to use more than 20, I've got to start doing essentially spills and fills to the memory space to reuse those registers. Yeah, questions on that? All right. Okay, so here's what PTX looks like, just to give you some concrete examples. There's some pseudocode in here that's sort of specifying what each individual element is. So you can specify a register. You can specify whether this is a predicate, so you can have registers that it knows are predicate registers, meaning that it's going to apply this to the mask of the executing SIMD instruction. So when we talked about branch divergence or control flow divergence, and you're having branches that you execute, and then they sort of go off in different directions, You can do that, and you can also do predicated instructions on GPUs. Predicated instructions are what traditional vector machines use, meaning that you point the machine at a specific predicate register that you've written to, and then it uses that 32-bit mask to decide which threads are actually going to do this instruction. And in this simple example, there's a predicated branch. So they've sort of pre-computed the condition on the branch in this very last line here, right? So there's this like set EQ F32 thing, right, which is basically testing inequality and then setting this predicate register P for every thread. And then they're doing a predicated branch so that only the threads where this equality was true are actually going to take it, and the rest of them are not going to take that particular branch. Memory instructions look a lot like memory instructions that you've seen in traditional ISAs. There are additional qualifiers for things like the size and the data type, like is this a float, is this an unsigned? There's also qualifiers that are in there to distinguish the different memory spaces, so that if I know this is a global load, I'll put that in the load and store instruction. If I know it's a shared, I'll do that. There are also generic instructions, but those require additional translation because now I don't know what memory space it points to. So I've got to try and figure it out through some translation mechanism. ALU ops look like every ALU op you've ever seen. There's adds, there's special, SYSCI-like instructions that do multiply and add. High and low parts of the registers. If you took 362, this should not be sort of everything about the predicate here should be, and when I say 362, I mean any machine, any class that sort of forced you to program at an assembly level, this shouldn't be all that foreign to you. So this is what the intermediate ISA looks like. Other questions on this? And you can dump your binaries. So the stuff that you did in your previous assignment that you've already handed in, you can run this utility called cuobject dump on it, and you can look at what the assembly instructions are for your particular program. Okay, so here's a concrete example, like the very simplest example that we have, which is this vector add example. And this is compiled, I believe, for a Volta machine, so slightly older now, but still relevant. So the PTX, so your vector add looks like this, right? This is the sort of simple statement. We're doing some couple of loads to global memory, and then a store to global memory in the actual code, in the CUDA code itself on the top right-hand side. And then it translates into this PTX. Let me just highlight a couple of things before we move on. Let's get this. Okay. So this is your CUDA. It gets translated into this. And then the sort of global memory operations here are in this particular statement, and you can sort of pick them out in this code. So like these are the two loads to A and B, and then this is the store. So these are the sort of global memory operations that are taking place. And then the math is sort of in between those two. And then all of the other business is just like loading parameters and computing addresses, okay? And one thing that you need to keep in mind about this ISA is that it is not explicitly vectorized. Like it's not like all of these instructions are implicitly vector, meaning that every one of these instructions, even though it looks like it's a scalar, like a normal sort of single core thing, it's actually happening across 32 threads in parallel across the warp. Okay, so every instruction essentially is vector inside this ISA. Questions on this? Okay, and then go ahead.
I was looking at the ISA, and there's a lot of read, modify, write atomic operations as well.
Yep.
When would we use that?
If you're trying to do some kind of synchronization primitive, or you're trying to update some shared variable, you'd use read, modify, write, just like in traditional CPUs. Typically, you want to do this on the shared memory. So if you're using these atomic read, modify, write operations, it's super efficient to do it on the local scratch pad. Because think about it, right? If you're taking 666 or you took 565, read, modify, writes are a pain in the butt. Why? Because you've got a distributed CPU with distributed caches. Now all of a sudden I need to coordinate my read, modify, write. I need to lock out everyone else from screwing with this thing when I want to mess with it. And it's all in the cache and it's all transparent to the programmer. So there's all this complexity to try to manage that. GPUs don't do any of that. Okay, they generally don't do any of that. At least they don't do it well, right? If you want to do a read, modify, write on a global operation, it is horrendously expensive, okay? Because you have to send it all the way out and all the way back. We're just not going to cache it, right? Essentially. But if you try to do a read, modify, write in shared memory, you are guaranteed there is only one copy of this thing. There is no replication like there is in a traditional caching system. So you know that Yeah, I can control the order of the operations right there on the core, and I know all the threads that want to mess with this thing are right there on my core. And I control the timing. They're all serialized through the access to essentially the load store pipeline that goes to the shared memory unit. Okay. So that means that you can do these atomic operations on shared memory and have it be visible to all of the other warps or all of the other threads in that same thread block in a super efficient way. Versus if you have this crazy distributed thing, you've got to manage copies in different places, which is really difficult. Okay, good question. Other question on the PTX. Is this in the 565 book? They have PTX instructions in there
Yeah,
now.
they have the whole instruction set.
It's not the whole instruction set. It's like its own book now. Like there's a website you can go see. There's a bazillion instructions and qualifiers in this thing, but they probably have the sort of reasonable subset of it. Okay, so this is what's inside your binary. And then this sort of finalization thing is going to take this, it's going to parse it, and then it's going to generate this. Now, what is this? This is the actual machine instructions NVIDIA calls SAS. This is the mnemonic for set instruction. This is the instruction address in the instruction memory space. And then these are the binary representations of the instruction. Okay, so in this architecture, the instructions are 64 bits wide. Okay, so this is the encoding of the instruction. And we can see that there's, there's a loose correlation between the PTX and the SAS, especially in this very simple, very simple piece of code. You can still pick out your loads and stores, right? So you have like this global load here. That's one of the loads. There's another global load down here. And then there's a global store down here. What does .e mean? I don't know. There's no documentation on it. I mean, we do kind of know extended load. That's what we think. But like, this is super well documented, the PTX. This is like completely undocumented, except for, a table that says MAD, performs fuse multiply add, full stop. And then 3/4 of the instructions aren't even in said table. Okay. Part of this is because it's secret sauce, and they're like, well, forget you. You have to use our finalizer. You have to use our software toolchain to even generate binaries. And why should I tell you what my secret instructions are? Because you're just a competitor anyway. And there's no sort of reason for them to open source it. So you don't really know what these instructions are doing. This is in contrast to AMD. AMD's actual machine ISET is open source. So you can know what the actual machine instructions are doing. Okay, anything else that's kind of weird about this code? Does anyone notice anything that's odd? Yeah.
Yeah. The number. Oh wait, I never mind. I guess the numbers on the middle column are addresses then.
The numbers on the middle column are addresses. Yeah.
Every blank line has a different notation.
What do you mean?
But the leftmost column is different for every blank line.
So the blank here, right? That's actually accounted for in the address space, right? If you're doing, it's like a whole instruction. It's another 64-bit thing, right? And it's blank. Like there's no instruction here. Why do you think that is? What are some reasons you might do this? You probably already know the answers, so don't answer. Why would I do this? Why would I have these holes? Like this is in the binary. I've got a bunch of ones and zeros, and I'm either not telling you what the instruction is or doing something else. Yeah.
Some weird hazard in the pipeline or whatever.
Weird hazard in the pipeline. So like a bubble, kind of like insert like essentially a no-op for bubbles. That doesn't hold with what he said though, that they're all actually different encodings. It'd be weird to have like, because like the first hole is whatever, 4E, and then the next hole is 3/8, right, in binary or hexadecimal. So they're different in some way. They're saying something different. Yep.
Like proprietary stuff they don't want to show.
It's all proprietary. So it could be that it's a proprietary instruction, right? So so basically I'm going to obscure your view of things. So every third instruction is magic. So I'm not even going to tell you what it is. It could be that. It's not. But that's what it could be. What else might it be?
Two instructions.
So that this instruction is bigger, right? Every third instruction is 8 bytes instead of 16 bytes instead of 8 bytes. It's possible. It's none of those things. So what this is doing is it's actually encoding the dependency information. So what do I mean by that? So in a CPU, in 565, when you do out of order execution, what is controlling dependencies? Reorder buffer is controlling, the in order commit. But for issue, what is controlling dependencies? The dispatch unit, which is using what? Physical registers, reservation stations, register allocation table, trying to match up this particular instruction depends on the result of this instruction, trying to find those dependencies. Okay. And what happens when you have a dependency in a CPU, you can't issue the instruction, right? If I do load use, I can't do the use because I don't have the value, unless I do some crazy value prediction, which never works. Okay, or usually doesn't work. So it has to stall. On an out of order CPU, what do you do when that's not moving? So I have a load, and then I have an add that uses the result of the load. What do I do on an out of order CPU?
Just have another independent instruction.
I just go to the next one to see if it's independent. If it is, I'm going to issue it. That's out of order execution. Out of order issue, meaning that I can skip over things that are waiting on dependencies and then do the other work after. That is the essence of what out of order execution does. GPUs don't do that because that's expensive as hell. And it only helps single thread performance, which GPUs have enough threads, so we say we don't care. So in a CPU, that's what's happening. In an in-order pipeline, let's say I'm not being aggressive and I'm not doing this register, like no rat, no sort of renaming, no sort of crazy physical register thing. What do you think would have to happen if I had a load and then a use? Those of you who took 437 should know this. You stall. How do you know it's load use? Hazard detection unit, right? I basically decode the right register for my load, and I decode the registers that the add is reading. And if there's a collision, I can't do anything. I have to stop, right? I have to stop the pipeline. GPUs are in order. Okay, meaning that that's essentially what happens. They do in order issues. So as soon as there's a load and a use, I have to stop. Now, 437's processor was super simple. Okay, in reality, if I want to do this at scale, detect dependencies at scale, I need a mechanism called a scoreboard. So you probably maybe heard of a scoreboard in 565 in the out of order sense, which was kind of complicated and esoteric and not really used today, but we still teach it to you. You can do an in-order scoreboard that is way simpler, okay? So if you wanted to control dependencies across instructions where you've got, out-of-order commit happening potentially in the GPU, you need an in-order scoreboard. An in-order scoreboard, if you want to do this dynamically, is kind of expensive, right? You have to basically keep track of dependencies in some table. That can become expensive. If I know the latency of every instruction in my code, I don't need to rely on dynamic dependency detection through this scoreboard, right? The scoreboard says, like, I issued this, floating point divide operation. It's going to take a long time. Floating divide is always going to take the same number of cycles in a sort of fixed. It's not like a memory instruction. It's going to be variable latency. So if I know that after I issue that floating point divide, it's going to be 20 cycles before I use the result, I can burn that into the binary. And that's what these magic lines are. These magic lines are encoding the dependencies of the subsequent chunk of 3 instructions to say how long I want each of these 3 instructions to stall for. Because I know that it's waiting on a production that happened 7 instructions ago. I know the floating point division pipeline is 17, so that I'm telling you to go wait for 10. These are literally encoded inside the binary to say, wait 10 instructions before you issue this next operation. And so if you do this for all of the instructions where you know that there are deterministic latencies, which most of the instructions are deterministic latency, then you can avoid paying the overhead of trying to have dynamic dependence detection and stalling logic. You just have to read the binary and say, all right, I know that this particular xmad, for example, or I don't know, what's a good example? So what's producing something here? Right, so let's say this is the production register, right? It's going to be used by this xmad. If I know the pipeline latency of this thing that's producing R2 is 7, I'm going to tell this next instruction to wait 7 after it's issued, and I'm going to encode that explicitly in the binary. And so that's what this is. It encodes essentially the dependence information of every bundle of 3 instructions. And it vastly simplifies the sort of internal dependency checking logic. Does this work for every instruction? What do you think? Yep,
Not for loads.
not for loads. Loads have a non-deterministic latency because you don't know if you're going to hit in cache. There's sufficient interference in the memory system, so even if you don't hit in cache or you do hit in cache, it depends how many other threads are contending for that bandwidth at the same time. So those things you do not know deterministically are going to take a fixed latency. And so they have special mechanisms to basically like, you know, if you issue a load, then there's some dependency sort of tracking on when that load comes back. And there's explicit like dependency tracking instructions that sort of get embedded to say like, wait until this load comes back before you can issue this instruction. And that gets encoded in there. And so there's some hardware in there to basically wait for loads to come back for the for just the sort of memory instructions where you don't know their latency. But for all of the sort of vanilla pipeline instructions, I don't need all this dependency crap. I can just encode this. And again, you can do this. You would never do this in x86. Why? Because now my binary says that my floating point unit is going to take 100 cycles. If I change the architecture, so now it takes 50, the binary doesn't work anymore, right? Which is a disaster. So because there's this intermediate step where I can recompile the code for any generation, I can leverage that back to encode as much information statically as I need to try and simplify the hardware design. And part of the reason GPUs got way more efficient is they didn't used to do this. The early GPUs had true dependence tracking, and it was costing them a lot of energy. And then they're like, well, we don't need this, so let's throw it away and just encode it in the binary. And it saved them, I don't know, 15, 20% energy efficiency by not doing all of this in dynamically because they didn't need to. Is there a question? Yeah.
So for every pre-instruction bundle, they basically say the instruction that sits at this address will need this much latency relative to the next bundle, basically, and that's the thing.
No, it's like what it basically, and so this is a lower bound too, right? Because you may be stalled additionally. Like if it takes more than this number of cycles, it's okay, but you cannot issue this before this number of cycles. Okay. So what will happen is it will read in this packet, this third instruction packet, and then it knows the minimum cycle wait for each of the subsequent 3 instructions. And then it will make sure that before it issues those, that cycle dependency has been satisfied. Make sense? And this is an older ISA. What they do now in Hopper, every machine instruction is actually 16 bytes wide. And they encode all this dependency information in each individual instruction. So instead of being like an 8-byte instruction that encodes, all the stuff that you would think they would need to encode for an instruction, they just encode all of the dependency information per instruction and just make the instruction super big, which is kind of a nightmare for iCache, but I guess they just deal with it. Yeah, but that's essentially how this would work. Yep.
So if we know how many cycles we're gonna stall for, can't we have another thread use the SM during the cycle?
Yeah, that's what will happen. So this is all from the perspective of all of the ISA, except for some special instructions that assume like synchronization things or warp synchronous instructions, which are kind of more fancy. This is all just from the perspective of one warp, right? The ISA is sort of one warp worth of work. And then you launch many different instances of this, and then you can overlap them. Okay. Other questions? Okay. And this is completely undocumented. Somebody has actually reverse engineered this for some generations. So there's this like tool that this guy, one of these guys working at one of these finance firms. Okay. So you'll find that there's lots of like really good technical people that work in finance because, it's important to do finance fast and they love GPUs because they can do parallel work super quick and sort of do their models fast. So they have an incentive to hire all of what they call quants. Have you heard like this term quants, right? So they hire these guys, you usually get paid way better. Although, the tech companies are keeping up, but usually they hire like super smart PhDs or master students from computer science, computer engineering, and then they go like fill divisions with these guys to try to make their high frequency trading stuff go faster because there's like a linear, if I can make this thing go faster, I can actually apply this algorithm and beat the other people trying to do HFT, and you make a huge amount of money doing this. And so one of these guys who worked inside one of these companies was like, okay, I don't like the way NVIDIA is finalizing my PTX and I can't do anything about it, so I'm going to write my own assembler. So I can write my own SAS, okay, and generate my own PTX. And if I do this, the guys over at, what Goldman Sachs aren't going to do it. And then we're going to be faster because our GPUs are going to be better and we're going to make N dollars. They actually released it open source for an older generation, but he reverse engineered it. He basically figured out what all the bits are. And so you can go, there's like some tech doc and you can download it and you can essentially write your own SAS for a limited subset of the ISA and run his executable and it will generate all of this. And how did he do it? Essentially trial and error. Just good old fashioned reverse engineering work to, go and I think NVIDIA hired him, actually. That's what happened. So after he did this and he published it, I think he ended up working for NVIDIA. So then he stopped. Yeah. So anyway, that's sort of how economics sort of play into this. Any questions on this? All right. Okay, let's move on. That's it. So that's it for sort of the core CUDA stuff that we're going to go through. Let me see. And if any of you are considering taking some of those jobs, I think that the general feedback I've heard from people is the money is good, but the work is soul crushing. But I guess you could do it for a while. Is there a way to present this damn thing? Full screen mode. Okay, who has seen this before? Nobody? Some folks have maybe seen it. Have you been through it? If you haven't taken, some people maybe took the class. Okay, so machine learning. When machine learning first sort of started coming out and people realized you wanted to use machine learning, you wanted to use GPUs for machine learning, people in the architecture community were sort of like uninformed. Okay, because it's like, how much do you need to know any particular workload? Like if you took 565, their spec, there's like 40 workloads in there. Like they all have these weird names. What do they actually do? I don't know. Right. But I know it's got bad misprediction rate. And if I do G-share, it gets a lot better. Like, so it's like the architects generally don't like learn about any specific application domain unless there's a really good reason to. Okay. And this sort of, it became very apparent when machine learning started to explode that we couldn't do this for machine learning. We had to understand the algorithm. We had to understand what was going on with these things. We're going to build specific accelerators that are just going to accelerate this one particular subclass of algorithm. We really should understand how it works. And so there was a tutorial that was sort of presented at ISCA. I think the first one was in 17. This is the slides here I'm leveraging from a presentation in 2019. That was like introduction to machine learning and why it's important to us for computer architects, okay? And so I go through this in this class to just give you some context, especially from the system level of, where this space is and why it's important to us. They wrote a book on this, so I put a link to it on Piazza. Sort of includes all of this material. It sort of goes through the basics of like, what the algorithm is and then what the specific core computational kernels that we care about are. Then it even goes into more specific machine learning types of acceleration, which we'll get to in the back part of this class. But this is important because your programming assignment is asking you to do, basically convolution, right? This is still true. You guys aren't looking at me like crazy. Like it's still, which part of the assignment does this? 4, it's the last one. So I think it's optional. So what is 3 again? What is 3 asking you to do? 3 is convolution, and 4 is optimizing it. Is that right?
4 is all the highlights.
All of that. Okay, 4 is actually kind of trivial if you do 3, but anyway. So, so we sort of point you at this stuff, but I want to give you sort of a tour de force on this before we go into it. When is the due date on 3? 2nd March? Okay, so a couple of weeks. So nobody's started it yet. All right. Or maybe like majority of you haven't. Okay, so this is put together by these folks at MIT. Joel Emmers is super famous architect. At least, fame is relative, right? So, super famous in architectural circles. He used to work for Intel for a very long time. He's a professor at MIT. And then NVIDIA basically poached a lot of Intel's talent, and he's been working there for like 15 years, I think now. And there's some other professors, Vivian Zay, and some graduate students that help sort of produce this. And so these slides are taken from them. Okay, so, the sort of motivation here, at least from, an academic standpoint perspective, is partially this, which is this plot of like how much research is being done and how much work is being done in the machine learning space, okay? The x-axis here is years, and the logarithmic no, it's not logarithmic. It's not logarithmic. The y-axis here is basically the number of machine learning papers that get uploaded to archive. Who's heard of archive? Okay, maybe most of you, hopefully, right? So archives traditionally, all right, let me give you a little blurb on archive. So traditionally, academics, we didn't like post our papers, right? It was like you did your paper, you were like working in your lab, it's this top secret idea, and like you don't want anyone to steal it, and like nobody hears about it until actually it's accepted at one of these conferences, which are super hard to get into. It's like sub 20% acceptance rates, okay? And sometimes it takes a long time to get into these things, and you get rejected, blah, 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 and PhD students know how this works. And then sort of something weird happened here in like, you know, the sort of late 2000s, and people were like, I don't care about that. I'm just going to post my work. Okay. I did this thing. It's really good. I don't want to wait for some bozo to tell me that I get accepted. I'm just going to post it. Machine learning has sort of like taken this whole hog. Like as soon as I've got an idea, I'm just going to post it. There's no vetting process on archive, right? Nobody even reads it. Okay. You can post it in your archive that is just complete absolute garbage. I'm actually surprised that they haven't just gotten a deluge of like AI generated papers on archives. Somebody trying to be malicious. But it's basically like a repository of completely open, completely unvetted work. Now, that being said, a lot of really good stuff still comes out on archive, and it comes out on archive first because it's quicker. So machine learning has embraced archive. Our communities have sort of embraced archive. There's all this double blinding and reviewing sort of gets broken when you do this, blah, blah, blah. So it's not really, people still do it, but it's not done as pervasively. But basically, if you've got a machine learning paper, you put it on archive first, and then you get it into NIPS or, whatever, or the machine learning conferences. So this is just showing, like, if I looked at how many papers are getting posted on archive, which is the primary sort of venue, if you will, for publishing machine learning papers, versus years, there's this huge uptick, right? And the rate in 2018 is like 100 new ML papers per day uploaded to archive. Okay, to give you some sense of like just the sheer rate of stuff that's being done in the machine learning field. Okay, so there's no way that a tutorial or a class or me talking to you for a couple of lectures can cover all of this stuff, right? 100 new papers a day, that's insanity. So what we will do is sort of cover the sort of, the sort of key sort of foundational things, the sort of early stuff to give you some idea of how this works. But obviously there is a lot of, this isn't meant to be like a comprehensive survey, right? I mean, we'll touch on transformers a little bit, for example, right, which are cool right now. They weren't cool the last time I gave this class. Those are shifting and changing, and certain things in machine learning like were sort of in vogue once and now not in vogue anymore. And if you propose an optimization to recurrent neural networks, like nobody cares anymore, right? Like these kind of things go in and out of fashion, very quickly because the space is moving, okay? The resources here, they have a book. This is actually released. So there's a website that's got sort of all this material. There's a collection of papers that they published on machine learning accelerators as well. Okay, so what is artificial intelligence machine learning? At a very high level, artificial intelligence is very broad, right? The science and engineering of creating intelligent machines. Well, what the hell does that mean, right? That's like every machine is like intelligent in some way, depending on how you squint. But it's sort of a very, when I worked at EA, we used to have people who did AI, okay? What do you think the AI is for, I don't know, a soccer game? What's that? The players, the brains of the players. Okay, what do you think that looks like?
Defense statement.
What's that?
Defense statement.
Defense statements? Sort of. So, okay, the sort of, the person who goes into AI and like we've had people like when I was making video, maybe this has changed, but when I was making video games, we had all kinds of smart people who wanted to go into AI because that sounds cool. Okay, I'm going to build a brain of all of these little guys that are running around trying to do stuff, right? And so you think to yourself, well, I'm going to put a neural network in every brain of every soccer player that's running around. And that you could have done that. When I was doing this job, it didn't work, okay? So nobody did, and it was computationally expensive. So the AI sort of boiled down to, if the opposite, so you would write like, if opposition player is within, 10 yards and rand mod 5, like I'm able to, that is what AI was, at least in video games. It probably still is to a large extent. Why? Because like you can't control what goes on inside these neural networks, right? If I want to go, have a game and have it be fun, I need to control what happens. I can't have these independent entities doing weird stuff. Like, it doesn't make any sense. You need to put sort of guardrails on it. So what I think this is called in sort of AI parlance is like expert systems. Like expert systems is sort of like a fancy way of saying a bunch of if-else statements. Where somebody who knows soccer sat down and like decided how this player is supposed to act in every scenario. And then when he does something weird, they go, oh crap, if the other player went that way, I need to do something different. Okay. And then some randomization thrown in there because, you can't hit the post every time, but you got to hit it sometime. That's sort of, so like that is broadly still under the purview of AI, but it's obviously less sexy and less satisfying than like training a brain to like run around on the field. Okay. Machine learning is a subset of AI. So this thing that I talked about, this expert system, is some dude writing if else. That is not machine learning. Machine learning is distinctly different. It's a field of study that gives computers the ability to learn without being explicitly programmed. What I described was an explicit program, okay? What machine learning does, what neural networks do, is not explicit. I set up this thing, I throw a bunch of data at it, and I let it like sort of train itself. And I haven't explicitly told it to operate this way, but it does. It figures out the best way to do it, okay? So it's sort of, again, very broad. Neural networks are a subclass of this, but it's sort of this branch of artificial intelligence where humans are not explicitly telling the machine what to do. Brain inspired means that the algorithm itself is, at least you can sell that it's inspired by the brain, okay? So an algorithm that takes its basic functionality from our understanding of how the brain operates. Like we have a machine, right, that does a pretty good job, like in general. I mean, I guess you could argue that, but the brain works pretty well. We can like study it and try and figure out what's going on inside of it, and then we can try to model that, okay? In the end, it boils down to gems, but, it's sort of like, it's attempting to do what's happening in the brain. And inside this sort of brain-inspired, there are different, we can talk about how the brain works. I'm over time. All right, we'll talk about brains on, Tuesday, okay? And I promise you this will get much more technical. It's kind of fun to sort of do this at the beginning, but yeah. Questions before I go? All right, I'll see you next week. I'll see you on Tuesday.
Professor,
Yeah.
Joel Emmer went to Purdue.
Yes, you're at here, right? Yeah. Yep, we have a number of people in the hardware industry who, like, quasi, academic famous, let's say, that have come through Purdue. Yep.
The more you know, what you think.